Hello, my name is Benjamin Hansen. I am a junior majoring in engineering physics here at the Colorado School of Mines, and I'm here to present my research on the assembly of microparticles and composite materials under combined electric and magnetic fields, mentored by Dr. Ning Liu and Qingru Zhu of the Chemical and Biological Engineering Department here at Mines. The primary focus of my research was on the asymmetric dimers that can be seen in the top left. Their synthesis, analysis of their activity under combined electric and magnetic fields, and the intrinsic qualities that could be manipulated in order to promote unique movement. In order to create the fields needed for our experiments, we used two pairs of Helmholtz coils for the magnetic field, one in the x direction and one in the y direction, and a function generator for the electric field, as all can be seen in the apparatus figure in the bottom left. A particular field much of my work was centered around was an AC rotational magnetic field parallel to the substrate. Due to the polarity of the dimers and their tendency to always want to align their dipole moments with the direction of the field, the dimers will rotate. This rotation can be seen in the video being played on the screen now. This graph in the upper center describes the rotational frequency of the dimers under different magnetic field frequencies. As we can see, up to a certain point the dimers match the frequency of the rotational field, but at a certain frequency they reach a critical point, and the rotation frequency decays from there. Our theoretical calculations had this decay approaching zero for all magnetic field strengths, but what we learned in our experiments is that due to the induced dipoles of the dimers and the phase lag from the field, the decay actually goes to some value proportional to the strength of the magnetic field. Another motion we were interested in was trajectory tracing, as can be seen in the bottom middle figure. For this motion, we used a DC magnetic field pointing in the direction we wanted the dimer to move, and an AC electric field to control propulsion, similar to that of a car with a steering wheel and an engine. This combined field resulted in the red path seen in the figure, with the green path being the coded trajectory. From both of these experiments, as well as the others conducted prior to my research, we were able to conclude that this project was successful in finding a method that can accurately and precisely control asymmetric magnetic dimers by using dynamic combined magnetic and electric fields. In the future, our group hopes to apply these methods to developing crystalline structures that can be used to make composite materials. Thank you very much for your time.